This question is a continuation of the question from the previous video. The question in the previous video dealt with rods that are being manufactured to have a mean length of 40 millimeters. So the setting on the machine is such that the mean length of rods produced is 40 millimeters and the standard deviation sigma is 0.2 millimeters. So this comes from the previous video. The operators want to check whether the setting on the machine is still accurate. They take a random sample of 10 rods and measure their lengths. The lengths in millimeters are given here. So what's happening is a sample is taken, and from the sample we want to check the hypothesis that the population mean is still 40, that the mean length of each rod is still 40 millimeters. Conduct a hypothesis test at the 5% level of significance to decide whether the machine's setting has become inaccurate. You should start by clearly stating the null hypothesis and the alternative hypothesis, and finish by clearly stating what you conclude about the machine. So the null hypothesis means no change. That means that the population mean is still 40 millimeters. The alternative hypothesis is that the machine's setting has become inaccurate. So the mean mu is no longer 40 millimeters. So what we want to do is use the sample mean. That's the mean of this sample of 10 values to test this hypothesis. So we need to calculate x bar as the sample mean. So we just have to add up all these values, 39.5 all the way to 39.6, and divide all of that by 10. So the sample mean is 39.87 millimeters. So what we will be doing is comparing the sample mean to our hypothesized mean and seeing if this value of 39.87 is significantly far from 40 or not. If it's significantly far from 40, we will reject the null hypothesis. By significantly far means we're talking about a level of significance of 5%, and I'll explain a bit more about that later. Now, rather than just telling you what to do, how to calculate this thing, I want to do the background. And the background involves the central limit theorem, which I've explained in greater detail in earlier videos. So I'll just remind you of what the central limit theorem says. It says that if we take sample means from a population, then sample means will follow a normal distribution with a mean equal to the population distribution that the samples are taken from, and a standard deviation equal to the standard deviation of the population distribution divided by the square root of the sample size n. N in this case will be 10. We have 10 values. So you've got to imagine lots and lots of sample means. We have only one sample mean here, 39.87. But that value of 39.87 will lie somewhere along this line. And well, if you can imagine repeating this over and over, taking samples of size 10, calculating means, keep on doing that from your population, keep on taking samples of size 10. But of course, when you take a sample, you have to put it back into the population, then take out another sample of size 10, and keep going ad infinitum. Then we would have a load of x bars along here, and the distribution would be a normal distribution. So under the null hypothesis, we're assuming the null hypothesis is true, then the mean is 40. The mean of our this is sometimes called the sampling distribution, is equal to the mean of the population. The mean of the population is 40. So the mean of all the sample means is 40 by the central limit theorem. So more accurately, I should say by the central limit theorem and the null hypothesis. We're assuming that the null hypothesis is true. This is the distribution that we have. So I can replace mu with 40, and I can also calculate sigma over root n. So also sigma over root n is 0.2 divided by the square root of 10, which is 0.06. A very important fact about normal distributions is that 95% of the values in this case will be values of x bar, lie between lie within 1.96 standard deviations of the mean. So the mean is mu is equal to 40. So 95% of the values lie between mu minus 1.96 sigma over root n and mu plus 1.96 sigma over root n. Sometimes that 1.96 is rounded to 2, but I leave it as 1.96, it's more accurate. Roughly speaking, we would say that 95% of the values lie within 2 standard deviations of the mean. The standard deviation here in this case is actually sigma over root n. It's not sigma. This normal distribution has a standard deviation of sigma over root n by the central limit theorem. Now, you saw in earlier videos how to transform a normal distribution to a standard normal distribution. A standard normal distribution has a mean mu of 0 and a standard deviation of 1. You saw that the formula for doing that, to get the z value, so these are the z values along here, this horizontal line here, we take our x values. Well, our x values in this case are actually x bar values. This is the distribution of x bars. We subtract the mean of this distribution is mu, and we divide by the standard deviation of this distribution. Now the standard deviation of this distribution is not sigma, it's sigma over root n. So let's just transform these three values here. Well, let's transform mu first of all, that's the easiest. Well, let's say x bar is 40. If x bar is 40, we will have 40 minus 40 divided by sigma. That's going to give us 0. That'll give us 0. So the mean of this distribution is transformed to 0. We explained that before. Now what about these values here? Well, if we take mu minus 1.96 times sigma over root n and subtract mu and then divide by sigma over root n, what do we get? Well, these mu's cancel out. We've minus 1.96 sigma over root n divided by sigma over root n. We just get minus 1.96. And if we transform mu plus 1.96 root n, what happens is we just use this formula, replace x bar with this here. The only thing that happens is this becomes plus 1.96. So you can see that 95% of the standard of 95% of the values of our standard normal distribution lie between minus 1.96 and plus 1.96. Actually, plus 1.96 is the same as 0 plus 1.96 times 1 divided by 1, where 1 is the standard deviation. Okay, so that's really just the same as this. Replacing mu with 0 because the mean here is 0, and the standard deviation sigma over root n is replaced with 1. That's all. So we get 0 plus 1.96 times 1. We don't actually divide by 1. And this number here is just 0 minus 1.96 times 1. So 95% of our z values lie within 1.96 standard deviations of the mean 0. Now we're interested in seeing where this particular value of x bar is, 39.87. What we do is we transform it using this here. Under the null hypothesis, there is a 95% chance that our transform value of x bar lies in here, between minus 1.96 and 1.96. So 39.7 is somewhere along here. It's a value of x bar. So to transform it, we use this formula here. So x bar is 39.87. This is the one we're interested in. So this is how you do the actual calculation. There's not much to it. We subtract the mean mu. The hypothesized mean is 40. We divide by the standard deviation of this distribution, which is sigma over root n. That's 0.06. So that's how you do the calculation. And what we now need to do is see where this value is. Where does it lie? Well, you can see here that it doesn't actually lie in this region here. It lies outside it. It's out here somewhere. So this is minus 2.055. Now, under the null hypothesis, there's a 95% chance that we would get a value in here. And there's a 5% chance that we get a value that's outside of it. So 95% of the area lies between here, and 5%, that's 1 minus 0.95, lies outside. So the area of this tail here plus the area of this tail here add up to 0.05. So that's our level of significance. That's the meaning of 5% here. So if the null hypothesis is true, there's a 5% chance that we'll get a value that's outside here, that we get a value that's either along here, that's less than 1 minus 1.96, or a value that's along here, that's a value of z that's greater than 1.96. There's a 5% chance of that happening if the null hypothesis is true, if this is true. So 5% is a small probability. That's our level of significance. So if we're getting a value that's either less than minus 1.96 or greater than plus 1.96, we reject the null hypothesis. So we reject H0. Rejecting the null hypothesis means that mu is not equal to 40, which means that we conclude that the machine is inaccurate. It's not producing rods to the specified length of 40 millimeters. So just to tie all this together and explain it a bit more clearly maybe, if the null hypothesis is true, in other words, if mu is indeed 40, then the probability that this, which is our z-score, x bar minus mu over sig divided by sigma over root n, is less than minus 1.6, or that it's greater than 1.96, is equal to 0.05. So the probability that our z-score is less than minus 1.96, so this would be our z-score. So this is our standard normal distribution. These values are called the z values along here. Or the probability that our z-score is greater than plus 1.96 must equal 0.05. That means that this area here in this tail plus the area in this tail here, the standard normal distribution in theory carries on forever, but it approaches the z-axis. Anyway, these two tails must sum to 0.05. So that's where the 5% level of significance comes from. So if we're getting a z value that's less than minus 1.96 or greater than 1.96, we know that there is at most a 5% probability that that can happen if the null hypothesis is true. But since 0.05 is a small probability, what we do is we reject the null hypothesis at this level. Okay, there's a chance that we're rejecting something that's true. There's a 5% chance or a 1 in 20 chance that we're rejecting something that's true. But since this is quite small, we just go with that. We just reject the null hypothesis. So in the question we did, we got a value of z that was somewhere here. We got a value of z which was minus 2.055. So the probability of getting that value, or any value in this region, is less than 0.05. So we reject the null hypothesis. So that's just kind of restating what I said earlier in a slightly different way. So there's a chance that the null hypothesis is true. There's actually a 5% chance that the null hypothesis is rejected, and that is true. But since it's quite small, we take that risk.